First I want to say I'm so glad to be here, and it's so great to see so many people that are interested in being innovators in Houston, Texas, because Houston, Texas needs innovators, and it's so ripe for that opportunity. We have the largest medical center on planet Earth. We've got Rice, we've got U of H, we have Texas A&M, kind of. We have Baylor College of Medicine, the UT Health Science Center. It really should claim its rightful place along with the West Coast and the People's Republic of Cambridge. And it's high time it happened, and these kind of events are, I think, a part of that. And this place, what a great idea, a space surrounded by bars where innovators and scientists and clinicians can come together and create opportunities and value. And I think this is going to be a very important hub for that sort of activity. And I just found out there's a wooden bowl by the door, and if everybody drops off your business card on the way out, they're going to draw one, and you'll get free membership for a month here. And I think it's a great opportunity, and I encourage everybody to become involved in this place. So I'm going to talk about innovation, and many of you have heard this talk, and to you I apologize because it's kind of the same talk. I update it every couple days. But this is my take on how to innovate, and it's my little course I call Medical Device Innovation 101. Because although for the first decade of my career, I was just trying to get my legs under myself as a heart surgeon and learn to be a competent heart surgeon and to primum non nocere, do no harm. But in the last decade or decade and a half, I've increasingly tried to ramp up my innovative efforts and develop new technologies, and it's something I really, really enjoy. And to that end, I'm going to show you my disclosure slide. I show you this for two reasons. One, just to show you, these are companies where I've either founded them or play a key role, or they use my technology, something that I've patented as their core patent. So I do a lot of this stuff, and the second reason I want to show this is because these in red I'm going to talk about today. And I cannot possibly be objective about whether my children are handsome or not. I can't be objective about these companies either. So if I make them sound like they're the greatest thing since sliced bread, know that I've probably lost some objectivity. That said, I will try to maintain equipoise, but I encourage you to listen with the appropriate filters in place, okay? Before I get started, I want to talk about this guy, Thomas Robert Malthus. Has anybody heard of him? All right, there you go. He was a very controversial figure at the end of the 1700s and wrote a series of 6 books about the fate of society and the impact of population. And they are real doom and gloom. And they're very exacting analyses where he looked at the amount of land on the earth that could support crops, and he looked at how much an acre could produce of foodstuffs, and he knew how much a human needed to be sustained, and calculated very accurately that when the population of the world exceeded 2 billion inhabitants, there would be famine, wars, and societal collapse. It's interesting because last year sometime the population surpassed 7 billion. And when you look at his calculations very carefully and break them down, they're not wrong. They were very exacting and took into account every possible variable. But what Malthus couldn't have anticipated were the incredible innovations and advances in the several hundred years after his death. We now can take an acre of desert and turn it into arable land. We have genetically altered crops that produce much more reliably and much greater yields. And we can keep that stuff fresh and transport it all over the planet. So 7 billion and counting, and we're all fine, or by and large. So innovation basically headed off this predicted disaster. Well, we've got another predicted disaster in medicine. If you look at how much we're spending on health care, it is increasing at a rate that is 3.4 times greater than our gross domestic product is increasing. And in the next decade or two, it becomes unsustainable and the whole thing falls apart. We can head that off, and we can head it off through innovation, coming up with better ways to treat more patients, cheaper, more reliably, preventing disease. And that is the future. So why be a medical device innovator? Well, altruism. Somebody's got to do it. It's not a nice to have, it's a must have. All of our futures and the futures of our children and our children's children depend on it. It's also, it can really dramatically affect your financial trajectory. If you have a successful innovation, it brings tangible rewards. But the main reason, I think, to be a medical device innovator is excitement. Excitement. You can feel it in the room. Wait, feel that? I think Nikola Tesla, one of my heroes, said it best. He said, "I do not think there is any thrill that can go through the human heart like that felt by the inventor as he sees some creation of the brain unfolding to success. Such emotions make a man forget food, sleep, friends, love, everything." And I think my wife and children will attest to that. You know, I go out in the garage and get working and stay there for 2 or 3 days. Well, I was very lucky. I did all my general surgery and heart surgery training here in Houston under one of the world's most prolific and important innovators, Michael E. DeBakey, who tragically died in 2007. But I was his last chief resident, did several hundred operations with him, and saw the fruits of his innovative efforts. And this is one of my favorite pictures of him. Right there, he's the very age that I am right now. He was 52 years old. He'd just come to Houston, and he was taking Dacron polyester from a fabric store, from Foley's, and sewing it into tubes. And then he'd go to the operating room and cut out the aorta, the largest blood vessel in the body, out of a young cow, and sew that in. He tried nylon, he tried cotton, he tried vinyl, he tried a number of different fabrics. It turns out Dacron polyester is the only one that worked, but he found that out and is the father of the vascular graft, the artificial tube to replace a blood vessel that's now done millions of times a year all over the world. An important discovery, but this picture strikes me a couple ways. If I took any of you in a time machine back to the 1950s when this was done and said, we need to make a replacement for something to replace the aorta in the body, how many people would say, I know, let's carve it out of wood, or let's make it out of plaster of Paris? Nobody. You all would take fabric and sew it into a tube, wouldn't you? You would know which fabric, but he actually went and got all the different fabrics, sewed them into tubes and tried them out and saw which one worked. And that's what makes an innovator. That's what makes an entrepreneur. They don't just talk about it, they roll their sleeves up and do it. And the second thing is how little you have to step out of the box to be in a brand new place that no one's ever gone before. And there are all sorts of places in 2012 as easy to get to as sitting down at your wife's sewing machine. And that's it. No. Technology giveth, and technology taketh away. Whew, that was a close one. Okay, so after I finished heart surgery training, I went to Harvard, to the Beth Israel Deaconess, and was on the post at the medical school, and I decided I wanted to be an innovator. And I was doing a lot of coronary bypass. Do you guys know what that is? Where you take veins from the legs and sew them onto the teeny arteries on the surface of the heart. And when I finished training, the only way you did that is you stuck tubes and hoses into the heart and put them on the heart-lung machine and stopped the heart. And while the heart was motionless, you opened these arteries that are about as big around as cocktail straws, about as big around as cooked spaghetti, and you make a little slit, and with the motionless, blood-free heart, you would put 12 little stitches to sew a vein from the leg or an artery from the breastbone to the side of the artery. Very meticulous work that heart surgeons take great pride in doing. But I had heard that there were some surgeons in South America that were doing it without stopping the heart, with the heart still beating. Because it turns out some of the risk of heart surgery is that heart-lung machine that allows you to stop the heart. And they thought they could get around it. And so there were 2 American surgeons who were doing this operation. I went and watched one at Johns Hopkins, and he had an assistant take a 2-pronged fork and mash down on the surface of the heart to hold it still. And he could hold that one little area still while Dr. Fonger, Jim Fonger was the surgeon, would sew it. And it looked really, really hard. And it seemed to me that it was crazy trying to do intricate heart surgery with a fork. A spoon seemed a much more likely candidate. Now, so I went, nobody had made a machine, a device, a clamp that would hold it in place, that would lock it in place without a person trying to hold it still. So I went and got spoons and cut them into various geometries and started doing a lot of animal experiments and got it working pretty well. And then I brought my chief down and showed him an animal experiment. He said, why don't you try it on a human? And here's an operative video of the first human operation using a spoon to hold this artery. This is the left anterior descending artery on the surface of the heart, still, while the heart beat underneath it. So this guy only had a cut this big. He didn't go on the heart-lung machine. I didn't stop his heart, and he went home the next day after his coronary artery bypass. Very exciting, very rewarding, and really cool because it was my first successful patent. It was my first commercial product. Genzyme Surgical bought it and turned it into this device. Now watch. I'm going to make a little cut in the artery. That's hosing. That's bleeding you can hear. Watch, I'll pull the rubber band down. It'll pull the artery up against the back surface, stopping the blood supply. If I were trying to sew to this, or this, or this, no way. But when you look at this little window, there's no blood and it's not moving. And you'll see there's the little cut in the artery. And when we wear these big surgical telescopes, it magnifies things 3 times. So what I would see would look more like this. So there's the close-up, and you can see I'm putting the little stitches around the periphery. So it was very exciting going through this process, developing this, see it go from a spoon that I carved up in front of my TV in my apartment in the North End to this commercial product that ultimately was used in several 100,000 operations. And it was so exciting for me at one point to stand in the back of an auditorium and see somebody at the front that I had taught teaching a whole room full of people that I'd never met, to see it have a life of its own, and I wanted to do that again. But I wondered, am I a one-hit wonder? Is this an acquirable skill set? Is this something that I can work on, like practicing the violin or learning to ride a unicycle? So I went right at it again. The next thing I did was a valve thing. So these are valve sutures. Heart valves, we sometimes will replace them. We cut the old valve out and sew the new one in, and we sew it in with pieces of string with a needle at each end and a little fabric square. The fabric square keeps the string from pulling through. And here, in this picture, this hole is where the old heart valve used to be, and I'm sewing this new artificial heart valve in, and I've gone around the circumference and very carefully spaced sutures. And so these 2 green ones are 2 ends of the same suture. These 2 white ones are 2 ends of the same suture, and you want to space them really close. So after I put this one in and put this one in, it's easy, but this one I have to put real close without actually sticking the last piece of string. And I watched myself and others put in valves and saw that every other stitch, we spent much more time getting it right. So what I did is I took a pack of sutures and combined them. So it was one long chain, but each needle had 2 pieces of string on it. So those 2 that had to be close together, I placed at the same time. So this became the next stitch suture device. Instead of putting 24 needles, it was 12 needles, and each one was the easy shot, and it took half the time. And at some of the live meetings, we would do this through satellite live, and we could put an aortic valve in like 12 minutes. It was great, and it still has an exciting life. So subsequent to that, I think I have about 140 U.S. patents pending or delivered, and a whole bunch and international patents on about 40 different projects, and I'd like to share what I have learned during that process, and I call this medical device innovation. I'm going to hit a couple big points, and then I'm going to go back and describe each. First, focus on an unmet clinical need in a field you really understand. That might not mean what you think. Think simplicity, and then my favorite is do the experiment. So what is focus on an unmet clinical need in a field you really understand? If you go out and talk to Jack Gill or any financial analyst or any venture capitalist, they'll say, well, these are the things to focus on: congestive heart failure, diabetes, gastroesophageal reflux, cosmetic surgery, home monitoring, disease prevention. That's true. Those are all the places where it's nice to innovate, but I submit to you that no one is a domain expert on all of those. In fact, most people, if you're lucky, are domain experts on one of them, if they're a clinician. So instead of trying to master a new area, just look at that little world where you live, the thing that you do every day, and find opportunities to innovate. So whatever you do, whatever your hobby is, whatever your passion is, whatever your work is, there are opportunities to innovate, and you are already a domain expert. Find something that's challenging or stressful that you have to do all the time, or something that's time-consuming. Like on that valve thing, every other stitch was more laborious, and I had to do it 12 times. I designed something that mitigated that eliminated that step. Identify a step that frequently goes awry and results in complication. If you're doing something, that point where you put your feet a little further apart and wiggle your shoulders and say, okay, I got to get this right, there's an opportunity to innovate, because that's a source of stress. If you're a domain expert and that's causing you stress, it's causing everybody else stress that's in that field. There's an opportunity to innovate and make that easier. Identify something in a procedure or your workday that you hate doing. That's all the big innovations in services, medical services, digitizing things, making outsourcing the parts of your day that you hate. So there's what unmet clinical needs in a field you really understand. Now this is a whole topic, in and of itself and warrants several hours, but picking a good project. I have so many friends that are up to their knees in a project that has no future because they didn't do this. They didn't think about the hurdles, the regulatory hurdles. They didn't think about leapfrog technology, stuff other people are working on that's going to make all of their hard work obsolete. You have to think about the market size. What are the dollars associated with this if it works? And think about the dynamics of the field. If the guy who's going to use this is at the end of the referral chain, it's not going to get to him. And so talk to somebody who understands this. This is something they talk a lot about in the Jack Gill course. This is key. A successful venture requires that you aim at the right target before you start. One thing that's increasingly important, though, is understanding the finances. Right now, the pressures to take healthcare costs out are greater than they've ever been before. So if you've got a new technology, it's got to make it cheaper to take care of patients. It's got to eliminate steps. It's got to do away with some complication that costs money. It's got to avoid some procedures or diagnoses. That's the key. If you've got a project that's going to make it some diagnosis less expensive to take care of, then you've got something hot. Okay, think simplicity. When I came down from Boston to join the Texas Heart, one of the reasons was they were now doing all this stuff with pumps and artificial hearts, and I thought that was the future, and that was going to be the next huge thing. And I still stick by those guns. And that's not from an innovator perspective or a business perspective. That's a science and fun. But some of the most simple ideas, people waited in line to say why they wouldn't work. Everybody knew they wouldn't work, and it turned out they worked great. And here's a bunch of them. Do you know what balloon angioplasty is? When you have a narrowed artery, you put a balloon where the narrowing is and inflate it and push it back. Everybody was sure that wouldn't work. Well, they do it 1 million times a year now in the United States alone. Balloon embolectomy. When you have a blood vessel that's clotted, in fact, a couple nights ago, I had a patient who clotted a subclavian artery. We made a little cut and dissected out the artery, and we passed the catheter down and inflated the balloon and pulled the balloon out, and it pulled all the clot out. We did that in both directions and was fixed. My friend, Tom Fogarty, who's now a billionaire with a B, came up with that idea when he was a medical student. And he took it to his chief and showed it to him. And his chief said, quote, "Only someone as junior as a medical student would not understand why this won't work." Turns out it works great, and it's being done every day, everywhere, all the time. It's huge. The percutaneous aortic valve replacement. Every surgeon, this is taking a valve, crunching it down, threading it up on the stenotic valve, and inflating a balloon, and not replacing the valve, just pushing the old valve to the side. I, and every heart surgeon I know, when asked about it, said, well, these guys have never seen a diseased aortic valve. It's a big chunk of rock. You're not going to be able to do that. Well, of course, you can do that. It's being done every single day in the United States. Percutaneous aneurysm repair. There's a guy named Craig Miller from Stanford who was inventing this. The idea, if you had an aorta that swole out like this, instead of subjecting them to a big operation, you'd thread a large stent covered with fabric in and deploy it and exclude the stent. And he came to Texas to present it at one of the Texas Heart Conference. And Denton Cooley introduced him by saying, from the sublime to the ridiculous. It's now $1 billion industry. Anyway, so just because it's really simple and you're sure it's not going to work, doesn't mean it's not going to work great. So this is my mentor now. This is O.H. Bud Frazier, probably the most prolific and well-recognized transplant and mechanical assist heart surgeon in the world. Mechanical assist means mechanical artificial hearts or mechanical pumps that assist the heart. And he's the reason I came back to Houston. In fact, tomorrow he and I are going to Cleveland. He's getting a Lifetime Achievement Award at the Cleveland Clinic. But we got, the two of us, right after I got down here, applied for a grant and got $7 million to build a continuous flow artificial heart. But one of the simple things that I came up with when I first started working with them is I saw, this is the HeartMate 2. It's this little turbine pump that they put in to assist patients with end-stage heart failure. It was developed in the Texas Heart Labs by Dr. Frazier. The first one was implanted in a human right after I came down from Boston and joined him. Now 10,000 of these have been implanted. But some patients, when they have real sick hearts, and you put this turbine that takes blood and pumps it through the body, it's almost like walking on crutches with a sprained ankle. After you do it for a year, you go, hey, my ankle's better. Some of the hearts got better. And he'd take the pumps out. And I watched him, or I actually helped him take 2 of them out, And it was a big bloody operation. He'd reopen the breastbone, dissect out the heart. It was a bloody mess. Go on the heart-lung machine, cut off this part of the heart and sew it up. And I thought, these poor patients have just gotten well enough that they can come off their pumps, and then subjecting it to this. And so I said, Bud, why don't we just make a cut here? Let's not open the chest and just take this part of the pump out and leave that part still on it, and we'll fashion a cork that fits it perfectly. We'll make it out of cardiovascular felt. It's already approved for implantation in humans. We'll take one of these rings that isn't sewed to the heart, the same one, and make it fit snugly in there. And so here is a patient through a little cut. The pump's been taken out. There's a felt cork being held in place with 2 sterilized band ties from Home Depot. And there's his chest x-ray. And now that's the way it's done all over the planet. Simple, simple, simple. Just somebody had to do it. Okay, my favorite part of Medical Device Innovation 101 is do the experiment, because that's where the real fun comes in. Dr. DeBakey at a sewing machine, you just got to roll your sleeves up and figure out a way to do it. And you got to do it cheap, and you got to do it fast and get results. And to do the experiment, you have to make a prototype of your device. The key to prototyping is keep it simple and use the MacGyver principle. Do you guys remember the show MacGyver? This guy that could make anything out of anything? Well, this is medical device prototyping headquarters. If you can't make it out of stuff in the halls and aisles of Home Depot, it can't be made. Either Home Depot or Toys R Us or containers from things from CVS or the grocery store, any part of any material that you can conceive, I promise you I can come up with in a couple hours by coming here. Maybe this cut obliquely, or this corner of this container, or a straw from a bottle of WD-40. It's all there. So this is the great example of Home Depot engineering. We got this $7 million grant to build a continuous flow artificial heart. Steve Parnas is in the group. He's part of our team. We've worked indefatigably on this for 6 or 7 years. But the challenge was these pumps Dr. Frazier had developed in the Texas Heart Labs over the first 25 years of his career. And the idea is your heart is so weak, it's not circulating the blood, you implant this giant thing like this. So it sits here, and it's a pump. It's got a diaphragm that goes, it's got one-way valves. It takes blood out of the failing heart and pumps it into the circulation. And you walk around with this huge thing, but you can go home and go back to an active life. You have a wire that comes out to a battery pack, but it sure beats being dead. Look how big it is, though. Look on this chest x-ray. It's a huge can in your belly. So you could only put it in the biggest patients, and the operation was a big operation too. Some of them didn't survive. But the worst part was this. It had to do that once a second. So the flexible membranes and a high torque motor and cams and followers. If it did it once a second, that's 100,000 times every day. That's 35 million times in a year. And this thing would last a year and a half, and it would fall apart. So here's this patient who's on death's door, gets this miracle new device, thumbs up, leaves the hospital, thanks doc, gets back to life, and a year later, he either dies or has to get an emergency heart transplant. So this showed that these machines could keep people alive, but there had to be a better way to do it. Well, our friend, Rich Wampler, he's a physician as well, good friend of Bud Frazier's and Steve's and mine, was doing a missionary fellowship in Egypt, and he saw 2 workers using an Archimedes screw to pump muddy water out of a riverbank. And basically, it was a long, like fusilli pasta. And when you crank it, it's like a moving staircase that moves water up and out of the river. And he said, wait a second, maybe I can use a turbine like this to pump blood. It may not be as physiologic, it's not heartbeats like the other machine, but it won't wear out. There's no flexible components, there's no valves. And so over the next 15 years, Frazier and Wampler, and this is before I was at Texas Heart, worked on a number of devices, and this was the culmination of all of them. This is the HeartMate 2. 10,000 of these have been implanted now. Dick Cheney had one. It's a rapidly spinning turbine, and like I showed you, it takes blood out of the ventricle and spins it around through the rest of the body. And they work great. There are a number of patients that have had these for 7 years now who couldn't get out of bed and walk, who are now completely normal with these turbines on. It's changed the world. Well, we got this $7 million grant to take 2 of these, or something like this, and make a heart replacement. So here's how they're normally used. So Frazier said, and look how much smaller it is than the old pump. and only one moving part so it doesn't wear out. But Fraser said, Billy, we have to figure out a way to make an artificial heart. So I went to Home Depot. So this is the predecessor device. It's a big pulsatile thing. It's an artificial heart, but you have to wear a compressor, a little machine that pumps air in and out, and this is what we were going to replace. So I went to a store and got Dacron, actually just down the street from here, a fabric store, and I cut it into little triangles, and I sewed those into cones, C-O-N-E, cones. And I went to Michael's, the hobby shop, and got some styrofoam little cones that they use for putting dried flowers in, and stuck it on there. And then this is drywall tape for putting up drywall, you know, on the inside of a house, and silicone adhesive for caulking your bathtub or your toilet or your sink. And by putting a lot of layers of this around that cone and mixing it with silicone, made this composite material that you could actually cut in the operating room. When you put needles through it, it didn't tear or leak. And the inside was perfect Dacron, just like Dr. DeBakey was sewing on his sewing machine. So we knew that blood would like it. And then we made a couple other parts, and with that, designed the continuous flow artificial heart. Half the best that technology has to offer, half homemade crap from Home Depot. And sewed it. Now I should say a couple things. Another resource that I now have is the world's greatest large animal lab. We have full operating rooms with heart-lung machines. We have ICU for taking care of animals post-procedure. And with those resources, we were able to take calves, take out their heart completely, and replace it with this device. This cow has no heartbeat. He's got no pulse. He's got no EKG. But you can say by all metrics, he is a happy, healthy cow. A molasses-powered cow. So this is one of the first continuous flow animals in the world. We've now done 65 or 70 of these. And about 50 cases into it, we met a gravely ill patient, and after careful deliberation, put this in a human. This is the first human to have no heartbeat, no pulse, no EKG. Very brave man. He was an engineer. He was basically dead. He'd had a cardiac arrest and was being sustained by a pump outside the body. He couldn't get a transplant or any other therapy. And after careful deliberation, we implanted the device in him. Tragically, you can see how yellow he is. He was in liver failure and kidney failure when we did the procedure. When the liver failure progressed, so much so that he couldn't maintain consciousness. And after 5.5 weeks, the family asked that we turn the device off and let him die. But it captured the world's attention and actually was featured in National Geographic, as you heard Will say. And I was very proud to see it on the cover of Popular Science, a magazine that I've been reading since I was 13. Anyway, reverse scaling in making your prototypes is very important. By reverse scaling, I mean if you have some difficult little mechanism, make it 10 times as big and make it out of poster board and styrofoam. That'll show you exactly, help you flesh out your ideas, help you communicate to engineers. This is a really neat device that Tom Fogarty, the guy that made the Fogarty balloon, conceived of. And I won't explain it in depth, but it was a device that would allow you to attach a graft to the aorta without putting a clamp on it. Here's this prototype. A pair of barbecue tongs, a guitar string, and some wire. Now, if the father of all innovators is allowed to make crappy prototypes like that, then I submit that we all are. I showed you this device, the neck stitch, right? Here's my prototype of that. It was yarn and styrofoam and spray paint. I actually took this to Washington, D.C., to the FDA, and demonstrated it to a room full of people that thought they were watching a puppet show. Still, it got the job done. This is where I got that inspiration, by the way. I was lying in the bathtub, adjusting the shower curtain with my feet, you know, like we all do. Anyway. This is one of my favorite quotes. To invent, you need a good imagination and a pile of junk. I'll bet you guys who are innovators didn't know that there is a great pile of junk that is there for the taking. Every medical device on the shelf, whether it costs $50 or whether it costs $5,000, has an expiration date on it. That's its shelf life. It has to do with the adhesives used and the packaging and the dyes. When it reaches expiration, some companies will take products back, but most don't. You got to get it off the shelves, and there are warehouses that will come and take the stuff away. And everybody says, well, they'll probably send it off to the third world. And some stuff actually is taken to the third world, but a lot of it is thrown away or just stockpiled. And you find the guy that has that warehouse, and you take him out deep sea fishing once or twice a year, And he lets you come and dig through boxes and take what you want. Look, there's CT scans and x-rays and ultrasound machines. And here's my wife and two of the guys that work in the lab digging through stuff. And this is a little closet that I have down in my lab with literally $20 million worth of stents, snares, guide wires, sheaths, balloons, and it was all free. So that's one of our most valuable resources. Although, Steve, I think you'll see that the stents are really depleted. I took 100 of them with me to Paraguay as sort of a thank you gift. I just got back this morning. Okay, keep an eye open for interesting technology in the non-medical world that may have interesting medical applications. This is the best. Anytime you see something new in any field, there's a medical application, and it's up for you to figure out what it is. Somebody will, and it's whoever comes up with it first. So here's examples. Brushless DC motors, these pumps, these rotary pumps like I showed you, you couldn't make those with regular brush motors. But about 15 years ago, they came up with microprocessor commutation of rare earth magnets, brushless DC motors, and this whole VAD space has taken off. Well, now these motors have gotten smaller and smaller, and the magnets have gotten more powerful. So now we're working on a pump that's so small, you can thread it through the blood vessels into the heart without opening somebody up. And this is the Minvast pump, something that Dr. Frazier came up with. But this is at my shop at home. This is a little microprocessor commutator. And you'll see this pump at the end of this long little ribbon. There's the pump, that little blue and yellow thing. It's about the size of your pinky. And there it goes, swimming through the water under its own propulsion. It's a robotic eel. But look at that. That little pump will pump 4 liters a minute. That should be enough to get somebody out of heart failure, right? And the way we envision it is we're actually going to take that whole pump, and this little wire will be up against the graph, and we're going to drive it down into somebody's heart through a sheath, through a 2-inch cut below the right collarbone. And it's going to go down through the vein, through the right atrium, and poke through a hole in the septum of their heart and sit in the left atrium. So you'll be able to have this as an outpatient and go home with 3 or 4 extra liters of flow, instead of going through the large operations that are required now for us to put these big pumps in. And so this is a project that we have great passion for and are working on very, very hard at the Texas Heart Institute. Here's an animal experiment we did. There's the turbine, and it's taking blood and blowing it into the left carotid. And it's that little device. Shape memory alloys, you know, nitinol. The development of nitinol and the expansion of nitinol properties has opened a whole new field. I'm going to talk about this, but all the wires and snares and things we put in the body are made out of nitinol. None of them would have been possible 15 years ago. This Kips Bay medical mesh, this is this cool thing that we're working on now. It's a metal mesh that goes over a vein graft from your leg to decrease the wall tension to make the grafts last longer. And we put 600 of these in Europe and just got approved to do a study in the United States. People have looked at this over the last 20 years because it's obvious manipulating wall tension is an important thing, but we didn't have the technology to make that very delicate chainmail. Well, now we do, and this is a very exciting thing. Here's a graph you can see with a mesh on it going from the aorta to the coronary, and when you sacrifice them, they're thin-walled and look much better than regular grafts. Advances in microprocessors and Wi-Fi, that's a whole nother topic, but it's changing the world. Pumps and pacemakers and things that through cell phones talk to centers and tell the wellness of the patient, so patients can be called in and you can intervene instead of waiting for them to get sick. It's going to change the world. It has big brother connotations and overtones, but still, it's very important. The rare earth magnets, these I've got a real passion for. Has anybody played with these rare earth magnets? They look like regular magnets, but they are incredibly, incredibly strong. Now, when I was a kid, this was a big, powerful magnet. You know, these big Alnico magnets, aluminum, nickel, cobalt. And my first experience with magnets were these. In fact, this one has teeth marks on it. That was on my refrigerator, my mom's refrigerator when I was a kid. But over the last 15 or 20 years, they've come up with these super, super strong magnets that are thousands of times more powerful than the magnets that I grew up with. And every 18 months, they come up with stronger ones. It's part of the process. And they went from being prohibitively expensive to costing $1 each or 50 cents each. They've gotten very, very inexpensive. And so I came up with the idea at one point of putting a magnet in the heart and trying to grab it from a magnet outside the heart. I was playing with them and I said, these are strong enough to work inside the body, and developed a way of taking the left atrial appendage, So the left atrial appendage is this little chamber on top of the heart that helps your heart beat and helps your cardiac output go in exercise. But in the 3.5 million Americans that are in a heart rhythm problem called atrial fibrillation, the top chambers just vibrate. And that long jalapeno-shaped chamber that used to be helpful suddenly becomes a big liability. Blood clots in it, and those blood clots break off, they can cause strokes. And so we know that it's good to take that out, but it requires a big operation. So we developed a way of sneaking up with catheters. So we're going to sneak up from your leg vein into the heart with a catheter and poke it through right here. And inside this catheter is a little magnet on a wire that we're going to put in this chamber. This is the chamber where the clots that cause strokes live. And we're going to thread a balloon over, and under echo guidance while we're watching, we're going to inflate this right at the opening. We say, there, we got it. Now we're going to introduce another magnet stuck through a catheter that we just stick through the ribs, so no incision, just a poke. And the two magnets hit together, and that's going to provide us a highway to take a lasso and go up and over the appendage. And we can do this in about 30 minutes, and we've done it on over 800 people now. In fact, at the big TCT meeting next month in Miami, we're doing 2 live ones on the big screen. So then we snare it down, and all we're going to do is leave a piece of string. We're going to take the metal and everything else out, so it was easy to get through the regulatory hurdles. You know, I talked about picking projects that have favorable regulatory hurdles. If you're just leaving a string outside the heart, your regulatory hurdles are much lower than if you're leaving an implant or something inside the heart. And so here's what the procedure actually looks like in real life. You do it under X-ray. There's the appendage. There goes the magnet. There's the balloon. This is the echo probe that allows us to watch positions of everything. Here we go. Yahtzee. There we got it. Here comes our little lasso. We're going to open it up. We're going to advance it. It's going to snake over the appendage. We know we want to get beyond the balloon because the balloon was right at the base. We saw it under echo. We inflate it. We tighten it. We disconnect the magnets. And then we drop off our string. We can do these in 30 minutes now. And we've done 50 or 55 of them, I guess, at the Texas Heart Institute. It's done in the cath lab, not in the operating room. Patients can go home later that day. What else can we do with magnets? Well, there's this one thing we do where we put feeding tubes in patients in their small intestine. We have to take them to the operating room. These are usually very sick patients. I thought, what if we could use a magnet for that? So I took a magnet and put it in the chow of an animal, and he ate the magnet. So the magnet's now in his intestines, and I've got a magnet out on his belly, and I'm pulling a loop of intestine around through his belly. Then I thought, well, wait a second. If it's a little Cheerio-shaped magnet, I should be able to hit it with a needle under X-ray. So now I'm in a loop of the small bowel, and I thread a wire in and a catheter with a balloon, and it's a feeding tube you can put in the intensive care unit. Now, there's a famous story about 2 cardiologists, Swans and Gantz, who developed a catheter that you thread in through the collarbone, up across the tricuspid valve, into the pulmonary artery. They put a balloon on it so it would float where the blood went. And so Swan said, do it on me. And he lay down and Gantz put it in, and then Swan and Gantz ran upstairs and got an X-ray and said, it worked. Well, I was really inspired by that story, so I ate the magnet. And I went into Dr. Frazier's office and said, look, and he goes, what are you showing me? I go, I ate the magnet, look, it sticks. And he said, sit down. Libby, we need a psych consult right away. And I also found out that one of the toilets in my house has some ferromagnetic components. This last project I'm going to talk about, I've got way too much material here, but this is something that I'm super, super excited about. And I'm sort of hyper-caffeinated and sleep-deprived right now because I just flew back from Paraguay all through the night and got here this morning because I was in Paraguay doing this procedure. And it's really, really neat. It's for making AV fistulas. AV fistulas are where you intentionally hook an artery to a vein so that you'll have tons of flow through a vein and it'll dilate up big like this. So when this patient with kidney failure goes to dialysis, the nurse can stick 2 needles in that and hook them to the dialysis machine. And that procedure, hooking the artery to the vein, is done about 100,000 times a year in the United States. But it's technically demanding, and it works about 60% of the time. The very initial idea to hook an artery to a vein was by two doctors who worked as phlebotomists at Bellevue Hospital. And they saw that every once in a while someone would come in after they'd been in the Korean War, they got shot or stabbed in the arm, and they would have one of these. That somehow they injured the artery and the vein just right, that they grew together. And I remember when I was in the emergency room seeing two patients that had that. So I wanted to come up with a way of hooking them together with catheters, to use a place where arteries and veins were close together. By the way, that's an ultrasound of my arm that they put in that animation. But here go the catheters, one in the artery, one in the vein. They've got magnets in them, so when we rotate them, boom, they lock together, and then we fire electricity and just blast the channel. And people say, well, what's going to keep them from just bleeding into their arm? Why would they just bleed in their vein? And the answer is, well, that's what they did in the Korean War, and that's what they did in the ER. That's what Mother Nature tells us. You got to listen to Mother Nature. So we designed some catheters. These were sort of kludgy. They had heat shrink tubing on them and some other stuff. And these are all tubes and catheters and wires from that room that the guy gave me for taking him fishing. And here I'm taking those catheters and threading them up the leg of a sheep. So there's a sheep artery. There we're in the artery. That little chest piece here, that's the electrode. These are magnets, magnets, there's the electrode. Now we're going to put one of these in the vein. There goes the guide wire in the vein. And here comes the catheter. You can see they stick right together. These two little pieces are right on top of each other. We zap electricity through them for about half a second and take them out. And you'll see when we inject dye in the artery, it fills the vein and doesn't go anywhere else. And that's a great technology if you're a sheep. Tragically, sheep have very bad insurance and rarely get renal failure. So we had designed something that worked really well in sheep. This was the next iteration of that. Now we've got an electrode that deploys, and it worked in a similar fashion. But then when we went to Paraguay and tried to do it on humans, we found that it kind of worked. The human anatomy didn't like such long, stiff components. Although we had some fistulas that we made, they weren't as good as what we saw in the animals. Some of them were okay, but it was hard to put in and hard to get them to stick together. Still, the patients didn't have any incisions. It was quick, and when it worked really well. So over the next 10 months, we redoubled our efforts. We made a lot of changes, made them more flexible, smaller, slicker, smaller wires. But the main thing we did is figured out Mother Nature. We looked in every book, every textbook that was out there for where there was an artery and vein next to each other in humans. And the textbooks had some ideas, but not great. So we took matters in our own hands. We went and bought a bunch of cadaver arms, human cadaver arms. There's cadaver parts, etc. on I-10. No, really from Anatomical Gift. And we took blue methyl methacrylate, like blue superglue, and injected it down the veins, and red superglue and injected it down the arteries. Jesse Rios in our lab did this, and then dissolved away all the tissue and got these wonderful, wonderful models. And we realized, right here. And we had Mother Nature's number. And here, actually, there's a catheter in the artery and in the vein. This is of a living patient. There's the electrode. You'll see that when we stimulate it, it stimulates the nerve, and her muscle will tense up, but she feels no pain. There we go. We just made the hole. Now we'll take them out, and we'll inject dye, and all of her veins light up, and you can see there's no extravasation. So here we're injecting the artery, and that's the vein we're going to dialyze her through. We did 6 of those. We came back a month later and angiogrammed them. 100% of them were patent. We went back 2 or 3 days ago and did 9 more. This is the way this is going to be done everywhere. It doesn't require anesthesia. There's no incision, and anybody can do it. Disruptive technology that I'm really excited about. Let's see, one other, I won't talk about that. Yeah, I will. Look, this is this material that we've been messing with. It's a reverse thermal polymer. It's a liquid at room temperature, but when it heats up, it turns into a gel, and we're now using it to control bleeding in heart surgery. You put it in and squirt it. It immediately sets up as a gel and stops all bleeding. You do your sewing and sew through it. When you're done with it, you splash some cold water on it, immediately goes into solution, goes through the coronaries, and you urinate it out. It's totally biosafe. Now that's another project I was involved in. Let's see, what else would I? How many of you know how to do 3D computer graphics, how to do 3D design. That's an essential tool, and it's gotten so easy. If you're in this game, even if you're not a core engineer, you need to learn it. Because my machine shop used to be this. I mean, this is where I used to do everything. This is my garage. I've got a mill and a lathe and some other things, but now this is my shop, my laptop. These programs cost $99 now, and they are incredibly strong. Anything you can design, you can have made for no money. These are devices. This is something that I'm doing with Marcy O'Malley at Rice. This is a image-guided ultrasound device for placing lines. This is a 3D printer. 3D printer prices have come down. Do you know about 3D printers? You take the thing you designed on there, you put it in here, it's got a laser and gel, and there's a million different kinds, but for very short money, you can make 3D parts of your files that you generated on your computer, and there is nothing more compelling than trying to raise money with this. It's a million times better than a sketch on a napkin. And we got to this stage for under $400, from the idea to designing it, to printing it, and putting it together. This, by the way, is a motor-powered ultrasound-guided device for putting catheters in veins. The idea is you've got an aiming ultrasound probe, and everything else is automated. So here, we've got a little channel running through this gelatin. We're actually, the ultrasound probe is at the front. We're going to put the crosshairs on the device and pull the trigger, and it does everything else. So there's a cross-section of the tube in the gelatin. We put the crosshairs on it, and we pull the trigger. And this is what you see. It's clear from the side, so we'll be able to see what happens. This is in my garage, by the way. Here's this clear-filled tube. Watch. There goes the needle. There goes the guide wire. There goes the catheter. So anyway, the idea of being able to move things along, move the ball along the field for no money is realer now than it ever has been before. Here's another project that Will Clifton actually was helping me with. This is the one-shot anastomotic device. So here it is in design, here it is in real life. It allows you to realize your ideas for short money and see them and make them and try them out. And here's actually, this is a movie that Will edited, I think it's here. This is us actually using it. So there's a beating heart, vacuum-assisted coring. There's a hole in the heart. Here comes an iteration of this device. We put it in, deploy it, fire it, lock it in place, and it allows us to hook one of those pumps up to the heart without a needle and thread, without sewing anything. And we think that's going to be the way it's going to be done. In fact, one of the major pump companies has just partnered with us to develop that technology. There's the turbine, goes into the heart. We think you'll be able to do it without going on the heart-lung machine. Anyway, I know that's a lot of material. I'd like to end with two quotes in a story. The first quote is one of the great innovators of all time. If you're not failing every now and again, it's a sign you're not doing anything very innovative. That's Woody Allen. And I guess I just have one quote, but here's a great story, and this story really resonates with me. You all know who this is, right? The Wright brothers at Kitty Hawk, North Carolina. In 1903, they're the first people to do controlled flight. Other people had flown, but they did wing warping, and they could actually change the direction. No one could do that before, and they became the fathers of modern aviation. Now, roll forward 5 years. It's now 1908. They sold exactly 0 planes. They spent a fortune of their own money, and if you asked anybody in 1908 what airplanes would be used for, they thought maybe it was for taking people up for rides and carnivals. Nobody thought it had any practical applications. But there was a young lieutenant named Thomas Selfridge, and he was a lieutenant in the Air Force. Yeah, they had an Air Force in 1908, but it was mainly balloons and kites. The idea is you would raise someone up in a balloon with some field glasses, and they'd say, okay, I can see the enemy coming. There looks like about 2,000 of them. They've got a cannon and a horse, and then they'd pull you down, and you tell them that. You couldn't let the balloon go because then you were a victim of the prevailing winds. They might not be going in the right direction, and even if they were, that you'd have no way of going back and reporting on what you saw. But they said, wow, with this heavier than air fixed wing thing, you could go out, you could go much further, you could fly over them, really figure out what was going on, and then you could come back and report. And while you're over them, you could drop stuff on them. So the military thought that maybe it had potential, and the senior military advisor for the Air Force was actually Alexander Graham Bell. and Lieutenant Thomas Selfridge convinced Graham Bell to let him go out and take a ride in the Wright Flyer. And so the Wright brothers, the Wright Flyer could only take one person. They spent money they didn't have and built the Wright Flyer 2. The Wright Flyer 2 could actually take 2 people aloft. And on that day, Lieutenant Thomas Selfridge traveled out to Fort Myer, and here's a picture of Lieutenant Thomas Selfridge taking a nice graceful turn. Those are his legs sticking out. Wilbur is actually flying. And right after that picture was taken, the propeller came off and shot through the right canvas and cut off the right wing. And the thing took a nosedive and hit the ground at probably 50 or 60 miles an hour. Wilbur got an open femur fracture and spent 8 months in traction, and Lieutenant Thomas Selfridge was instantly killed. But we have airplanes, and the Wright brothers are the celebrated fathers of aviation. So I think that's a story for all innovators, that everything you try to do in business or innovation or new devices or new drugs or anything, you're going to meet obstacles that look totally unsurmountable. You just roll your sleeves up a little higher and put your feet a little further apart, pump your team up, get everybody jazzed, and figure out a way around it. It is the innovator's life. If you let it get to you, you're done. Just know that there is no obstacle that can't be gotten, that can't be surmounted, and that is what innovation is all about. I thank you for your time.